Aditi. Okay. Thank you very much, Aditi. As you've heard, the the ability to isolate atomically thin crystals has made it possible to change the electronic properties of material without changing its chemical composition by alternative means such as twisting, such as stretching, shearing, etc. So I'm going to give you two examples today of how we can produce what we call flat bands, flat electronic bands, where the electron-electron interactions are enhanced and give rise to very interesting correlated phases. Let's get started here. So since its first isolation in 2004, graphene has created a lot of excitement, and it has amassed this long list of superlatives: strongest material ever, completely impermeable, highest current density, highest electrical conductivity, and so on. And in fact, there were a whole bunch of applications that are already available that use graphene as its basis. For example, composite coatings. You might have a bicycle that has a graphene in it, or a racket. Very interesting biological application. There's an artificial cornea, for example, artificial retina that a friend of mine is working on, extremely sensitive sensors that can detect a single molecules. Very excitingly, it's filters that can filter, that can, for example, do desalination. And these are basically incremental things to what we already have, but there are these big dreams, and in the future of the elevator to the moon and the 1 mile high building and a lot of futuristic kinds of possible application. So on this background, it's not surprising to see an ad that looks like this, that really epitomizes the excitement about graphene, where this company, Graphene Platform Corporation, that is trying to sell you graphene, is putting carbon as the next in line to this long list of iconic material that basically change our civilization. It's not clear whether this excitement is justified or not, but from my point of view, this is not it's not carbon that is really the transformative material. It is really the dimensionality of the material. It's the fact that we have a two-dimensional material. And in fact, since graphene's discovery in 2004, many dozens of new materials have come online that are strictly two-dimensional, that have a whole list of very interesting properties ranging from semiconductors to insulator, boron nitride here, topological insulators, superconductors, magnets, and all these are strictly one atom or one molecule materials. And if you stack them one on top of the other, you can actually create a completely new kind of material that would not be possible if you were just trying to synthesize it chemically, because they wouldn't be stable. And in addition to these dozens of materials that have already been realized and used in the lab, there are thousands that have been predicted to exist theoretically. So it is a really new era of the way we think about materials. Now, if I told you this story like before 2004, you would probably have called me a liar. And the reason is because people believe that two-dimensional long-range order cannot exist in nature, and the reason is simple. If we live in a three-dimensional world, two long-range fluctuation in low dimension, two-dimension, one dimensions are energetically favored, and they increase and therefore they increase the entropy, and therefore they would win. So people believed. And that's because they did not read the fine print of these papers, that since there's no long-range order in 2 dimensions, we cannot have 2-dimensional magnets, no 2-dimensional superfluid, no superconductors, and in particular, no 2-dimensional crystals. And in fact, it was very, very hard to sell the existence of such material to the community in those days when the papers were first published. So here is a simulation to illustrate what is meant by this. Here we take 400 carbon atoms, you put them in a box, and you digitally heat them up to 2000 Kelvin, and you just watch what happens. And it is fascinating to watch this. And what happens, they jiggle around because of the temperature, and then they form a buckyball. And you see a ball here that is stable. They form a ring that is more or less stable as well. But no matter how long you watch it, you will never create a really 2-dimensional crystal. And this is the basis of the fact that long-range fluctuations are cheap, and therefore they would be entropically favored. So this is when Kostya, Eva Andrei guy, where we're sitting around and think, okay, but we do have 2 layers material. We have these van der Waals materials that are strongly bonded in plane. They have covalent bonds in plane, and they have van der Waals bonding in between the planes. And we know that we can actually exfoliate them. So the idea is to just think like a conjurer's deck of cards, take your deck of cards and pull out a single card, and that will be your 2-dimensional atomic plane. So in fact, this is how they did it. They actually tried. You take this, let's say, graphite or any other kind of 2-layer material, you pick up a piece with Scotch tape, and then you bring it together and make it thinner and thinner and thinner every time you bring this tape together, and you break the material into 2 pieces, another 2 pieces, and so on and so forth. And you end up with something that looks like this. You put it under the microscope, and you go hunting for the lightest shadow here, and then you can measure it with an atomic force microscope, and eventually there's a good chance that you will find a monolayer graphene. This is how we still do it in my lab today, although now there are techniques, chemical vapor deposition, for example, where you can grow these layers in vast sizes, like meters long and even more. Okay, so why is this interesting? Let's talk about correlated states. Now, everything that I'm going to tell you now, which is about graphene, which is still the queen of 2-dimensional materials in terms of what we can do with it, because the other materials are still in their infancy. So I'm going to tell you about the electronic properties of 2-dimensional materials. And since this is a colloquium, and I don't know if we have anybody out of the condensed matter here, but I'm going to tell you just a quick overview of the standard model of condensed matter physics. So if you take a crystal, so you have a Bravais lattice of perfectly ordered atoms here, the band structure, every atomic level gives rise to a band in this to an energy band. The electrons that can move across this crystal can be described by a block wave, which is made out of 2 pieces, a plane wave here with a wavelength that has to be larger than interatomic spacing, and then you can put this in the reciprocal space here. Every point in this reciprocal space would correspond to every atom in the crystal gives you 1 point in reciprocal space. And then you have another piece here, which encodes the topology of this wave function. And we're going to discuss that a lot in the rest of the talk. And there are two energy scales that are involved here. One is the kinetic energy, which is hopping from one atom to the other. We label it by T, and this is what determines the bandwidth. It's proportional to this bandwidth, the width of the energy of this band. And the other energy scale is the interaction energy, which tells us how much it costs to put two electrons on the same atom. And this is the interaction energy that may give rise to a correlated electronic state. So in one limit, when the interaction is very weak, you get a band structure that is parabolic, energy versus moment is parabolic. Basically, the electrons behave like free particles with an effective mass that is just given by the curvature of this band. Now, if you take my electrons and throw them in there until I run out of electrons, the highest momentum that they'll have is called the Fermi energy. The highest energy, the highest energy of the electron is called the Fermi energy. So the Fermi energy separates free, unoccupied states from occupied ones. So this is basically, they behave basically like free electrons, and they're free to move in this lattice. The other limit is when the kinetic energy it's less than the interaction energy. And this is when things become interesting, because then the band is no longer rigid. So by throwing the electrons in there, you can actually change the band structure. What will happen, the electron will attempt to lower their energy by opening a gap at the Fermi energy and create something where they become correlated, and you can get various correlated phases. For example, so if you get a flat band, which in other words, kinetic energy is much less than the potential energy, we have large degeneracy, and you can create various correlated phases like ferromagnetism, Mott insulators, charge density waves, fractional quantum Hall effect, superconductivity. This is when things start getting interesting. So if we discuss superconductors in the standard BCS theory, the critical temperature of superconductivity is exponentially suppressed in the pairing interaction density of state. So traditionally, if you want to get a superconductor, high temperature superconductors, what people try to do is to increase the density of states. And traditionally, what you do it by doping. For example, if you dope graphite by carbon, you can get it to be superconducting at about 6 degrees Kelvin. You dope molybdenum disulfide or tungsten disulfide with an ionic liquid. People have actually achieved critical temperature as high as 15 Kelvin. But then in the early 90s, started by a Russian group and in the group in Finland, especially pushed by Volovic, they were thinking of an alternative approach. Let's flatten the band, in other words, decrease the bandwidth or the kinetic energy. And in that case, it turns out that the critical temperature is no longer exponentially suppressed, but rather proportional to the interaction energy times the density of, and the density of state, of course, diverges in a flat band. So this is wonderful, and it led Volovic to speculate that, in fact, by using this strategy, we would be able to get to room temperature superconductivity. And he actually thought that there was evidence for that in work by Ashkenazi, for example, where you get graphite to show some evidence of superconductivity. But there is a fly in this ointment. Is this actually possible? Okay, you can get maybe the pairing, the temperature where the pairing occurs between Cooper pairs to be very high, but is it going to be useful? Are we going to have a critical current? Now, if you look at a London equation, where it tells us the critical current the supercurrent density is proportional to the superfluid weight. A here is the vector potential. So if you have a flat band, the superfluid weight is inversely proportional to effective mass, when the effective mass basically it's inverse curvature of the band. So if the band is flat, the effective mass goes to infinity, and the superfluid weight goes to 0. So even though you have Cooper's pairs, there will be no supercard. So it's kind of useless. No Meissner effect, no zero resistance. So pretty useless to have a flat band. So then is this when this paper that was led by Päivi Torma in Finland came to the rescue. And what they discovered is that this term here, the topological term, can save the day. And why is that? If you have a non-trivial topological band, if you have a block function that is topologically non-trivial, so you can think of it as a Möbius strip and with a bunch of kinks. Every kinks is an integer number, and this is something that cannot be undone by any kind of defect or impurity. It turns out that that gives an additional term to the superfluid weight, which is a geometrical term, which is basically proportional to the number of kinks in this wave function, which we call a Chern number. This is a topological invariant. So if you have a flat band with non-trivial topology with a finite Chern number here, then the superfluid weight has a lower bound. It's bound from below by the Chern number. So now we have a recipe to go to high temperature superconductivity, flat bands plus topologically non-trivial band structure. So this brings us to graphene, and as an example, graphene, as you all know, has a honeycomb structure, which is not a Bravais lattice. And as a result, it doesn't have this beautiful parabolic band structure, but it is more, it is actually very different. The band structure looks like this. The low energy band structure it consists of two cones. Red here is conduction band, blue is the valence bands. At charge neutrality, the Fermi energy is exactly here at the apices of the cones. And the slope of the cone is the Fermi velocity of the quasi-particle, which is proportional to the hopping here, T, nearest neighbor hopping, T, or the kinetic energy, and to the lattice spacing. And this is about 300 times lower than the speed of light. Very importantly here, we have two cones, and they are related by time reversal symmetry. They have an inherent chirality, which can be seen here by looking at the Hamiltonian that describes the electrons in graphene. So it has sigma dot p here. This is basically the Dirac-Weil Hamiltonian. Sigma here is a Pauli matrix, but instead of operating on spin, it operates on the sublattice degree of freedom. Here, graphene has two sublattices, one with the red atoms, which we call A, and the other one is the B atoms, which we call the blue atoms, which we call B. Each one of these, each sublattice is a Bravais lattice. So we have two interpenetrating Bravais lattice, and that is why the band structure doesn't look like a nice parabola. That is why it has this strange shape. A few things to note here. These are massless Dirac fermion. They're massless because the energy is linear in momentum, just like for photons or neutrinos. They have opposite helicity here. Sigma dot p, of course, is the helicity operator, and this has it's clockwise, and this is counterclockwise, so they cannot scatter from each other. Another thing to note here is that the ingredients that go into this band structure are two-dimensional honeycomb structure and two identical atoms per unit cell. In other words, none of these ingredients, which are necessary and sufficient to give you this band structure, requires to have carbon. So in fact, as long as you satisfy this geometrical condition, you can create this band structure, and then you can do it with other atoms. You can do it with microwaves, with cold atoms. There are many, many other realizations of this effective band structure. Now, the conical band structure gives rise to a linear density of state, which vanishes here at the at the Dirac point. And if you make a device, this is a standard device. So here you have graphene, you have a gate here. Then this is basically a capacitor where the graphene is one of the capacitor plates. You apply voltage between the two plates. You can change the position of your Fermi energy. Start out, let's say Fermi energy is at charge neutrality at the Dirac point. You apply a positive gate voltage. Fermi energy is in the conduction band. Negative gate voltage, Fermi energy is in the valence band, and it takes very little of amount of voltage to actually move this Fermi energy. Like 1 volt of gate voltage gives you a huge move in the Fermi energy by about 80 milli-electron volt, which is 800 Kelvin. Now, what happens when you apply a magnetic field? So magnetic field, it's a curl of vector potential, and the momentum goes to the canonical momentum. So now instead of the P here, we have P minus the vector potential here. And what happens is that the band structure breaks up into these Landau levels, discrete Landau levels, which are flat bands essentially, as flat bands as you can ever hope to create. And the energy here goes like the square root of the magnetic field and this Landau level index. The density of state correspondingly has peaks at each one of these levels, and it looks like this. And now let's talk about the topology of these bands. So these bands are flat. Are they also topological? Yes, they are. And this is how we can see this. Let's say that we take a sample. Now these are the Landau level as a function of positioning the sample. This is the left edge and the right edge. Because the electrons cannot get out of the system, the Landau levels bend. So the Landau levels bend up or down depending on whether in your electron or hole system. Now you throw in electrons and you bring your Fermi energy into a gap here between Landau levels. What happens? It intersects the edges. It creates really one-dimensional states which run along the perimeter of your sample. You throw in some more electrons. Now the Fermi energy is in the gap in the middle of the sample, but it intersects the edge states at the edges. And we have another one-dimensional channel. So now we have two-dimensional channels. So when you apply a current, the electrons are going to run across the edges in these two distinct and spatially separated levels. And if you measure the hole conductance, you're going to find that it has steps. So every time you enter into one of these gaps, you have the conductance is only through these channels, and it is quantized in fundamental units of conductance, E squared over H. And the multiplier here, C basically counts number of channels. So every channel produces 1 unit of conductance multiplied by the degeneracy of that channel. So for example, here we have two channels that are occupied, one that is 4-fold degenerate and the other that is 2-fold degenerate, because half of it is going into the whole factor. So basically, by looking at the quantum Hall effect, you can see that you immediately see that you have a non-trivial topology. So this is probably the only way to determine the topology of a band. So here we have flat bands plus non-trivial topology. Then Waalovic tells us that we should have room temperature superconductivity. But there is a problem here because these flat bands require having a magnetic field. And as far as we know, magnetic field and superconductivity are not, in most cases, not compatible. So the question is, can we do this? Can we achieve flat bands with a non-trivial topology without breaking time reversal symmetry, without an external magnetic field? And yes, the answer is yes, it can be done. And of course, we can produce flat band by just impose an external periodic potential. And that immediately breaks up the band into smaller pieces here. And then you're going to have, it's going to become narrower and narrower. But this is kind of obvious, but not necessarily useful, because we also want non-trivial topology. And in fact, this can be done in two ways, at least. So for example, if you apply periodic strain, it turns out that strain, if the strain can give rise to a vector potential, and if it has a curl, it gives rise to what we call a pseudomagnetic field, which has opposite sign in the two valleys. And that gives you perfectly flat bands, and that looks exactly like Landau level. They're called pseudo-Landau levels, which inherently have a non-trivial topology. Another way is to superpose two graphene layers. It doesn't have to be graphene. And when you reach a particular magic angle we're going to discuss, you get a flat band, which is equivalent to the n equals 0 Landau level. So this flat band is a pseudo-Landau level. So not only it is flat, but it has a non-trivial topology, as we will see. There are other ways of achieving this with line graph lattices, which I'm not going to discuss, the Dice lattice, Kagome lattice, Lieb lattice, and this is a whole field in itself. One can, these are a few references to these kinds of, the band structure for these line graph lattices. So experimentally, how do we detect whether we have flat bands, or how we detect Landau levels? We do it by scanning tunneling microscopy. So when you bring a sharp metallic tip to the surface of a sample and you look at the tunneling current here, it has two contribution, one that's exponentially dependent on the distance between the tip and your sample, by rastering the sample, you can actually visualize the position of the atoms, and this is what graphene looks like, that in a topography image of topography or STM topography. Another technique is to realize this density of state here sits in this integral here. So you take the derivative of the current with respect to the bias voltage, and that extracts the density of state. So by taking the derivative of the current, the dV here with respect to bias, you can get the density of state of in graphene. And here you see, this is, in this case here, we have a whole doped graphene sample. So the Dirac point here sits right at the minimum of this V shape, and the Fermi energy is defined as the zero at the zero of the bias. So for example, an experiment like this, you can separate the physics of the Dirac point from that of the Fermi energy. And then you apply a magnetic field, you see the Landau levels pop up beautifully. By fitting this sequence here of levels as a function of field and Landau level index, you can actually extract the local Fermi velocity. The line which gives you the quasi-particle lifetime. You can extract coupling to the substrate. So let me start by how do we create flat bands with strain? So when I showed you pristine graphene, the hopping, the nearest neighbor hopping was equal to each other. But we can actually, when you introduce strain or you stress the material, these hopping, the nearest neighbor hoppings are going to depend on position, and then you can just expand VF here. Remember, is proportional to T to the hopping. It turns out when you expand it in the position here, you get an effective gauge field here that looks exactly like a magnetic field, like the vector potential, except that it comes in with opposite signs in the two valleys. So a strain gives rise to a vector potential, which, if it has a finite curl, gives rise to a pseudomagnetic field with opposite signs in the two valleys. So you have something like a magnetic field, but no broken time reversal symmetry without actually having to apply an external field. And for example, this is what it looks like. So these are the components of the vector potential, and I can write them simply as linear combination of the hoppings of the nearest neighbor, of the different nearest neighbor hopping. And for example, this is when you have a triaxial strain, you can get an actual pseudomagnetic field that has opposite signs in the two valleys, but also remember, because we're not breaking time reversal symmetry, the net flux has to be zero, so it'll point one way here and the other way around it. So you have you must have a net magnetic flux of zero. So in terms of the density of state, now here we have the two cones with opposite pseudomagnetic field pointing. However, the density of state depends on the magnitude of magnetic field. It doesn't care whether the magnetic field points up or down, so the density of state will look essentially the same. A very interesting, an electron is going to see, if you shoot an electron in, is going to see the pseudomagnetic field, and it's going to respond accordingly. Now, there's something very special happening in the n equals 0 pseudo-Landau level here. And this is actually also true with an actual magnetic field, that for the n equals 0 level, the wave function in the k valley sits uniquely on the a sublattice, and the wave function in the k prime valley sits on the other sublattice. So the wave function there is a locking, a sublattice valley locking, or in other words, the electrons on the electrons on the red side are going to see a field up, electrons on the blue side are going to see a field in the opposite direction. And you will see how we can see that in STM. Okay, so our first attempt to do this was we prepared a bed of nails. Here we have pillars sticking out, sitting on boron nitride. We put graphene on top of them, and then we stretched it. So we stretched it across the pillars here, and that gave us a strain field, a periodic strain field. And here you see a micrograph, SEM micrograph is what it looks like. Here are the pillars. We have folds here, that a network of folds that connect the pillars. And if we look at take the density of, measure the density of state, or the STS spectrum here, we see that we have these peaks developing, where we recall at the Dirac point we had a V shape, we had a dip. Now we have a series of peaks which we can fit, and we find that we have a pseudomagnetic field here that is given by the sequence of the peak, which is of the order of 8 Tesla. So this is kind of okay, this is very nice, but if you want to get to room temperature superconductivity, or we can get even to superconductivity, it's not enough. And if you look at theoretical calculation, in order to get a superconducting gap, we need to do much better. We need a pseudomagnetic field of, for example, 400 Tesla, and that will give us with a period of 8 nanometers, here the period of 2 microns, that will give us a TC of 11 Kelvin. So not good enough. But then we tried something else. To do this, we borrowed an idea from mechanical engineering. So it turns out that if we have a thin, stiff membrane subjected to a biaxial compressive stress, what happens eventually, the membrane is going to buckle out of plane. And which way? And it will create a periodic structure. And what kind of periodic structure it creates depends on the stress, of course, depends on the substrate, depends on various parameters here, and here are example of simulations. Here are example of actual membranes that have buckled into these different patterns here. So, graphene is the ideal stiff membrane. It's one of the stiffest materials known. It is one of the thinnest, it is the thinnest material known. So let's see what happens. Can we actually create this kind of stress? It turns out that we can, and this was kind of an accidental discovery. So when you put graphene here on a substrate, and as everybody who's tried it, you always have ripples. And when you do some thermal cycling, these ripples collapse, and if they are pinned to the substrate, they will produce a compressive stress. And indeed, this is what happens. And we got these two collapsed ripples. And inside here, we had this beautiful buckling mode, hexagonal buckling mode. And this is a zoom into it. And this is the height profile along this line here. And you see that we have a buckled membrane. The period is 14 nanometers. The height is 1.5 angstrom of the modulation. And we have periods ranging from anywhere from 8 nanometers to 26 nanometers. And this is a 3D view of our buckled membrane. So the first thing that we did, we went to these crests here and did the spectroscopy. And sure enough, we found these pseudo-Landau levels. And when you fit them, you get a spectacular pseudomagnetic field of about 108 Tesla. And remember, this is the n equals 0 field. Remember, the wave function is sitting either on the one sublattice or the other, depending on whether the fields point up or down. And also remember, if the field points in one direction in the crests, it must point in the opposite direction in the valleys. In other words, we will have a separation of the wave function. And when we do the topography on the crests, we see that the wave function is sitting only on one sublattice. We no longer see the honeycomb structure. This is really a triangular sublattice, telling us that the wave function is sitting in one sublattice. And when we go into the valleys, the wave function is sitting in the other sublattice. It's pointing the other way. In other words, we have a separation of the pseudomagnetic field, a spatial separation of the pseudomagnetic field. And the pseudomagnetic field here we calculate is about minus 80 Tesla, of course, because the area is much larger here. However, this is still not enough. When we bring the Fermi energy within the n equals 0 Landau level, we see a nice opening of a pseudo gap, but we are not there, not superconducting yet. So the one place where superconductor was seen was in magic angle twisted bilayer graphene, and that brings me to this last topic here. Any questions so far, or shall we wait till the end?
Can I ask you, the way you presented this procedure of buckling the membrane, it looks like you deposit membrane on the substrate and then keep fingers crossed to discover which kind of period you obtain. Do you have active control of the amount of buckling that you obtain?
No, we don't have active control over anything. So this is something that needs to be figured out. No. So yeah, fingers crossed always helps.
I see. Okay.
So between these two folds, we get a range of periods. So the further away you are from the apex, the larger the period is. So we can study various periods. However, it would be really nice to be able to control this and to do this in a less accidental form. Yes.
Thank you.
Can I ask another question about the strain? Is it spatially uniform, or it's modulated?
No.
Also, does it have one period, or do you have to consider also higher Fourier components in your?
So locally, it has the same. First, of course, it's not uniform, right?
Yeah,
The strain. And in a single sample, you get several pieces. So the period kind of changes with distance from the apex. So it is not a single period, and there is a relationship between, because as you go further out, the stress decreases, so the period increases. So no, it's not a single period.
So you have to consider that
Locally, we have large regions of the same period, so it kind of changes very slowly, but it is not a single period, yes.
So can you think of it as then a field that's somehow varying a little bit spatially on the?
Yes, absolutely, yes.
Oh, thank
But
you.
how big is the coherent region of it, which is pretty homogeneous in its?
It's about many of these periods. Okay, so it's about 10 or 20 of these periods. So it changes very little over. So the whole regions was about 600 nanometers. So it changes slowly enough for us to be able to make a statement, but it's not perfectly controlled or anything.
Thanks.
Okay, so let's move on to twisted bilayers. So as you probably already have all seen this, you take a layer of graphene, put another one on top, and you twist it. You create a moire pattern with a period that's inversely proportional to the twist angle. And what happens here, this bright region here correspond to what we call AA stacking, where every atom in the top layers has a neighbor in the bottom layer. And the darker regions correspond to AB or BA stacking, where in one case, the A atom in the top layer has no neighbor, whereas the B atom does have a neighbor, and vice versa in the BA stacking. So it's basically an interference pattern. What's interesting here is that electronically, the AA configuration is the most energetically costly. It's about 20 milli-electron volt per atom. So it really does not like to form this AA configuration, whereas the AB and BA are much more favorable. So in fact, when you have very small twist angles where the periods are very large, you see that these AA regions will shrink to about 10% of this moire unit cell because they are energetically so costly. And for the same reason, we have the AA regions are a little bit higher than the other regions, and also density of states has a maximum on the AA region. And this is what makes it possible to visualize these things, to see these things in an STM topography and spectroscopy. So now this brings us back to way back 2009 when we first discovered this. So here we have a piece of graphene, chemical vapor deposition growing graphene on a TM grid, transition electron microscope grid, and you zoom into it, and this is the gold rim here, and here we have graphene, and in this region here, we have single layer graphene and many twisted bilayer graphene, and we have every possible twist angle that you can imagine. So without changing samples, we have a zoo of different twist samples in the single sample here. So when we first looked at it, we looked at the topography and then we looked at the spectroscopy. Here we have 20.8 degrees. You can see that by the period and also by taking the Fourier transform. And here you see the density of state, which kind of looks like the single layer graphene. But then as you reduce the twist angle, you see these peaks appearing, which look like Van Hove singularities. And as you reduce the twist angle, they get closer and closer together. And finally, when you get to about 1 degree, they kind of merge. And also you see a gap opening here right at the Fermi energy. So when we plotted this gap, the size of the gap between these peaks as a function of twist angle, we saw that it kind of goes to 0, not at 0 degrees, but at 1 degree. And at the same time, by doing Landau level spectroscopy, we could also measure the Fermi velocity, and we saw that it decreases as the twist angle decreases. So so basically what we have here is the creation of a flat band, slowdown of electrons, which means that correlations are going to be enhanced. So in order to understand why we create this flat band here, it's useful to look in reciprocal space. So this is the reciprocal space and the Dirac cones for the bottom layer in green, the top layer in red. And when you look at the Brillouin zone, you see that you create 2 mini Brillouin zones because of the super period. And what's interesting here is that the Brillouins here on top of the superlattice here is generated by the K values in the bottom and top layer. So they have the same chirality. And whereas the Brillouin zone, the mini Brillouin zone at the bottom here is created by the K prime, so it has the opposite chirality. So we have 2 mini Brillouin zones. We have 8 orbitals per unit cell, which correspond to 2 valleys, 2 layers and 2 spins, twice the degeneracy of a single layer graphene. So how are these flat bands created? So here's our Hamiltonian that corresponds. This is for the K value of the 2 layers here. If there's no interaction if there's no tunneling between the 2 cones, just go through each other. However, when you allow them to tunnel into each other, we have a tunneling term here, and we have a hybridization that gives rise to a saddle point in the band structure, which produces Van Hove singularities in the density of state. Now, the distance between these Van Hove singularities depends on the twist angle minus the tunneling probability. So you see immediately that as you decrease the twist angle, there's going to be some point where these 2 cones, these 2 Van Hove singularities are going to merge. And that happens at the so-called magic angle. And it's very simple to show that it's basically given by the ratio of tunneling, interlayer to intra-layer tunneling. So basically, it's really, you can think of it, it turns out that it's when the time to tunnel between the layer is comparable to the time to tunnel between Moiré unit cells, that's when you get this flat band. And this is what it looks like at the magic angle. And what's interesting is by just a change of variables, one can show that this Hamiltonian here at the magic angle looks like this. So you have effectively a vector potential that is created by the Moiré sublattice. And this is just for the K value here, for the K mini Brillouin zone. So here you have this sits on the A sublattice, this valley here, and this valley would sit on the B sublattice, and you have opposite pseudomagnetic fields on the A and B sublattice. So basically, you have created the Moiré superlattice gives you a pseudomagnetic field, essentially, and if you put in some numbers, it's huge. It's about 120 Tesla. So, and everything is reversed in the K prime value. So pictorially, we can illustrate it like this. So these are the 2 mini Brillouin zone, and you have pseudomagnetic fields, which are it's pointing up on the A sublattice and down on the B sublattice in the K values, and the whole thing is reversed in the K prime sublattice, mini Brillouin zone. Okay, so we have basically 4 quantum numbers here. So in one mini Brillouin zone, pseudomagnetic field points up on the A sublattice. In the other mini Brillouin zone, pseudomagnetic field points down on the B sublattice. Okay, so this brings us now to the experiments. So fast forward to 2016, people figured out how to actually control the twist angle. Didn't have to wait for accidentally having a twist angle. This was done by this group here from Texas A&M. And using this technique, the group by Pablo Herrero discovered that this at the magic angle material goes superconducting when you have 2 holes per unit cell. So you have an insulator here flanked by 2 superconducting domes with a pathetically low superconducting temperature, less than 2 Kelvin. At the time, it was even less than 1 degree Kelvin. And this would have been the end of the story had it not been for the observation that we have an insulating phase flanked by superconducting domes. And in addition, you have very strong coupling here as measured by the critical temperature over the Fermi temperature. And people immediately realized that this is very similar to the phase diagram of high temperature superconductors, where you have antiferromagnetic phase here flanked by 2 superconducting domes. Now, notwithstanding the low critical temperature, what was remarkable is that whereas the high temperature superconducting phase diagram, every point on this phase diagram is a separate sample. You have to fabricate a separate sample, to synthesize a separate sample. So it's very difficult to go from one point to another. Whereas in graphene, all you had to do is change the gate voltage by throwing in more or less electron. So you can create this phase diagram in less than a day. And people said, okay, there's so many similarities, maybe there would be others. For example, is there a pseudo gap phase sitting right above the superconducting dome? Is there nematic order or any kind of ordering in this pseudo gap phase? Is there a strange metal phase with Planckian dissipation? So this actually stimulated a huge amount of work where people were trying to find out whether this can shed some light on high temperature superconductors, which is still a mystery, and whether we can find pathways to bring the critical temperature up to much higher temperature, maybe similar to high temperature superconductors. So this stimulated a huge amount of research, both experimental and theoretical. Now, on our end, we made such samples and decided to look at them by scanning tunneling microscopy. So here is a magic angle twisted graphene layer. This is the topography. These are the AA regions. And then you go into the AA region and look at the spectra, at the density of state as a function of gate voltage here. Here we have the gate voltage. We have a negative gate voltage, so the Fermi energy is sitting below this flat band. And we see this flat band very nicely showing up here. And then you change your gate voltage to this is about plus 60 volts, where the Fermi energy is above the flat band. So here we have an empty band, here we have a full band. In both cases, the band structure looks pretty much the same. So of course, the next step is to bring the Fermi energy into this flat band. And this is what happens. Okay, this is half full band. You get a splitting, you have a pseudo gap. Everything becomes much broader, interactions really kick in. Now, when you do the same thing, so this is for a half filling, which is 4 electrons in this out of the 8 electronic states are filled, or you can also say that the Fermi energy is at what used to be the Dirac point. Now you can do the same by throwing in either. This is so, you know, there's a matter of nomenclature here. 0 here means that the Fermi energy is right in the middle of the band. -4 means that the band is empty. +4 means that it's full. So we have, let's say, when -4 electrons, we have a gap. Then you throw in 1 electron, or you have -3 holes. You see a little pseudo gap. -2 or 2 electrons in there. So every time you have an integer number of electrons, you open a little pseudo gap. So you see this action here, and it's really happening at every integer filling of this band. In other words, the band is kind of malleable. You throw in an electron, everything changes. And that has to do because of interactions are important here, and the kinetic energy is suppressed in the flat band. So what we see, one thing that we see is we can do charge spectroscopy on this state here when the Fermi energy is in the middle of the band, and you see that spontaneously the system breaks up into charge stripes. Red here corresponds to 1 electron per moire, and blue corresponds to 1 hole per moire. So you have alternating plus and minus charges that happen spontaneously. And this is at the temperature of 4 degrees. It's above the critical temperature. So of course, it's reminiscent of the charge nematicity that people see in high temperature superconductors. So what's the scorecard now? So let's compare high temperature superconductors to magic angle twisted bilayer graphene. So we do have a pseudo gap phase, and we have nematic order. However, there are more than 2 superconducting domes. It actually turns out that almost between every integer filling, there's a superconducting domes, whereas in high temperature superconductors, we only have 2. The insulating and superconducting phases are competing rather than being intimately connected as in high temperature superconductors, and the jury is still out on whether or not we can learn anything about high temperature superconductors from twisted bilayer graphene. Now I'm okay. I can just stop here. I have 3 more slides on the topology of the flat band, but maybe we should quit here and do it if you want to see this.
I don't mind hearing. I mean, I think you can take some more time. The topology story, at least for me, is very interesting. So
okay, so let me tell you a little bit. Okay, so we said that we need flat band plus topology. We've shown that there is a flat band. Is it also topological? So and we've seen that this eightfold, this flat band is eightfold degeneracy. The degeneracy is protected by what's called C to Z times T, so 180-degree rotation or inversion in plane times the time reversal. So these eight bands, mini bands here, are completely degenerate here. So even though you have the pseudomagnetic fields pointing up or down, because they're degenerate, you cannot reveal the topology. So you have to do something in order to reveal it. So now these pseudomagnetic fields give rise, they're real fields, they give rise to diamagnetic currents. And it turns out that they give rise to, that they actually separated in phase and they're opposite in direction. So you have chiral currents that are either clockwise, which correspond to a Chern number of +1, and currents that are anti-clockwise that correspond to a Chern number of -1. So of course, if all levels are filled, the Chern number of this band is going to be 0. No topology is going to be revealed. So the band has to be partially filled. You have to break one of these symmetries. Okay, so we have Dirac fermions that are coupled with opposite pseudomagnetic fields that are generated by the Moiré potential. So we can actually label the 8 states by the valley, by which one of these mini Brillouin zone it is, by the valley, by the sublattice A or B. This shouldn't be just B. And by the Chern number. So we can label these 8 states, and this is what they are. Here up, the arrows correspond to spin up or down. So you see they have alternating Chern numbers, plus or -1, depending on whether it's red or rose or blue here. Okay. Now, how do we break the symmetry? So there's two ways of breaking. If we want to break the C2, the inversion symmetry, what we need to do is to have a staggered potential. So boron nitride is actually very interesting. It's a sister material to graphene. It has almost the same lattice constant, except that it has different atoms in the different lattices. So if you put your graphene right on top of the boron nitride, you've broken the sublattice symmetry. And by doing that, the A atoms have a lower energy than the B atoms. So you see the pink atoms here are lower in energy than the blue ones. And then you start throwing in electrons. And if you're partially filled, if you have an odd, and depending on how you throw them in, if you have an odd filling, for example, you will certainly have a finite Chern number, and that will give you an anomalous quantum Hall effect. A quantum Hall effect which you can get without an external magnetic field. The other way of breaking the sublattice, the symmetry, is by applying an external magnetic field. There you break the time reversal symmetry, and now all the states that have a Chern number of +1s or that are aligned with the magnetic field will have lower energies, and the states with -1 will have a higher energy. Again, depending on how you throw in your electrons, you will have you will get a finite Chern number, so you will get a topological band, which will give rise to superconductivity, which will allow superconductivity to take place. And here are the experiment. One is an experiment initially done by the group of Goldhaber-Gordon, where you break the sublattice symmetry with a boron nitride substrate, and you see beautifully, and then by the group of Andrea Young at Santa Barbara, and you see that you have, as you change the magnetic field, you see that you have anomalous quantum Hall effect around 0 Tesla. It can be either +1 or -1 in units of h/e². And these are our experiments. Here we have, these are transport experiment. We apply an external magnetic field. And again, we see that we have a quantum Hall effect that is just develops perfectly well on each one of the integer fillings. So when you have 3 electrons, for example, and in the electron sector, or 7 electrons of filling, you get a Chern number of +1. If you have 2 electrons, a filling of 2, you get Chern number of +2, and so on and so forth. And as you see here, so you see every time you have an integer filling of the band, we don't see it very well at filling of 1 or -1. You break the time reversal symmetry, you reveal the topology by seeing quantum Hall effect. And this brings me to the summary. So I've shown you that we can get flat bands by using strain. Graphene on pillars, we're able to get 8 Tesla with these pillars. And then buccal graphene, we get huge pseudomagnetic fields of about 100 Tesla, but not yet enough to give rise to superconductivity. When you have twisted bilayer graphene, you can create pseudomagnetic fields. They're about 120 Tesla, which are generated by the Moiré potential, and which are equivalent to an n = 0 pseudolambda level that have C2 times T symmetry. In the partially filled band, you always break, one can break the symmetry and reveal the topology, and as well as allowing superconductivity to emerge. So this is just the tip of the iceberg. There's so many results that are just pouring in right now. There's really much more to come. Go beyond 2 layers. When you go to 3 layers already, there is a spectacular new ways of producing superconductivity in graphene. when you have the bottom and top layers align and the layer in between is twisted by 1.5 degrees. Again, you get superconductivity. But there's a whole plethora of van der Waals material that are just waiting to be explored. So stay tuned. And here are the people who did the work. Top row are the people whose pictures you've already seen. The bottom row are students who are working on other projects. Here are our Japanese collaborators who provided the boron nitride. Andrei Geim's group provided the niobium diselenide sample where we saw the buckling. Theoretical collaborators from Francois Peter's group helped us analyze the buckling, and Christian Haule, who helped with the charge nematicity. And thank you for your attention.
Okay, thank you for a wonderful talk. So, are there any questions?
Like, I have a question. If there's, that was really great, actually, and beautiful STM work. It's gorgeous. I think I missed something important at some point in the talk, probably because I drifted off. How does what's the mechanism of this superconducting state within the high fields? You mentioned that you need something like 400 Tesla to get a superconducting state.
This is a very good one. These are the theoretical calculations, and what they're assuming a superconducting coupling. They're assuming the U, okay? And they just start from there. And where do they take this from? They take it from remember when you intercalate graphite, you can, with calcium, for example, it goes superconducting at about the highest TC, I think, is 11 Kelvin. And from that, they extract a U, and they take it from there. So it's not some independent mechanism. They just use the U from there, and then they just crank out the Bouguereau of de Gene, and they get.
Could you put down their equation? I mean, could you show their equation again? I just wanted to see.
Whose equation?
The equation for the high TC for the graphene.
For the buccal graphene? Oh, the equation at the beginning.
Yeah.
Olovik. Yes. Okay, so this is a standard equation, but this is if
what I don't get, I sort of remember it, but what I don't get is how do you get TC out of that? Because you're looking at a ratio of energies and you're getting an energy.
Oh, here it's H bar omega D. So that you need the Debye frequency is a prefactor here.
Okay, but then you'd think it would be limited to that. What's the Debye frequency for graphene? Is it way above room temperature? I guess it is.
Yeah, that's usually above temperature. Yeah.
I see. So it's limited by the Debye frequency or whatever.
No, I mean, this is no. This is way smaller. This is an exponent. I mean, okay, in order to get, and this is only valid when U is much smaller than T. Okay, so
which are you looking at? The bottom one?
I'm looking at the top one.
No, that one's fine. What about the bottom one?
Oh, the bottom one. Okay, so here it's proportional to U times the volume of the flat band in reciprocal space. Okay, so if you have a super period structure, the volume of the flat band keeps shrinking.
But I'm looking for an energy, because this is just the ratio of energies, and TC is an energy. So I wanted to know what's the above in your conventional one. It's omega Debye or sometimes EF, depending on what theory you're using.
Okay, this should actually be U times the volume of the reciprocal space of the flat band in reciprocal space, because U times rho will end up being dimensionless, right?
Okay, so it's
volume
U times the density of states over T. Is that what you're saying?
Right.
Okay. I was looking for the extra factor of energy. So
Okay, I'm gonna have
so
to put that in.
U
for
is
the
what
next-
dominates. U is what gives you the high temperature.
That's right.
that right?
That's right. So,
Okay.
you know, I mean, so Volovic, so there was, I don't know if you know about that, there's experiments by Ashkenazi on graphite that are, you know, kind of controversial. And where they claim that they saw superconductivity in a piece of graphite, and what Volovic argued that this is possible if you have a helical kind of defect in graphite. So, and he showed, and this, you know, if you read, his papers are beautiful, are just really elegant. He showed how this can lead to high temperature superconductivity, but you know, I mean, it's very difficult to, I mean, it has to be a lucky accident to create this kind of defect. It's a screw, it's called a screw dislocation, which you know a lot about, right?
I know somewhat about them.
How do you create a network of screw dislocations in graphite? So if you can do that, Volovic shows that you can actually reach above room temperature superconductivity. I don't know, you know, not everybody takes that seriously.
Okay.
See if there are no other questions, I could follow up on the field. Is the field, does the direction matter? I mean, I'm worrying about vortices and so on. If you have this huge field on your
You mean the pseudomagnetic field?
yeah, the pseudomagnetic field, does it generate vortices also, or is it a fictitious kind of field?
So in order to generate vortices, you have to be kind of type 2 superconductor. You have to expel, you're right, the magnetic field. So you're asking whether energetically having such huge, no, I mean, this is not a real magnetic field.
Okay.
So how does one show this? No, well.
So I was thinking maybe the direction matters in the sense that it would be something like.
No, I think this is a very good question. So I haven't thought about this. So because we haven't gotten to superconductivity, but yes, is it gonna? That's a very interesting question. Is it going to increase? Is the fact that you have a pseudomagnetic field going to increase the energy, right, of this state? Yeah. And
I guess I should
I
look
have to think about it. This is really a good question. Yeah.
I'm going to look at those papers. That's very interesting ideas.
The image of the nematic correlated electronic structure was really striking to me. I'm used to having that sort of thing be something you imagine in correlated materials and maybe see sort of fleetingly, but not have strikingly visible like that. How difficult was that image to get, especially given that you need to like pass current in through the tip and you're seeing regions with one electron here, one electron there?
Okay, so I mean, how do you actually get the charge? I mean, out of an STM measurement. So okay, so you know that we measure density of states, and we know where the Fermi energy is. We know where the band edge is. Let me get to that slide. Okay, here. Okay, so density of state is a function of energy, Fermi energy sitting here. So now if I have Fermi energy here, I know where the band edge is. If I integrate from the band edge to the Fermi energy, I know what fraction of the band is occupied and what fraction is empty. And we know that there are 8 electrons per Moiré cell, right? So you can fit 8 electrons per Moiré cell will fill the entire band. So that allows me for to calculate the charge by just taking the integral here. So what we did here, we set inside. So you take, I mean, this is quite tedious, but you do this for every point on this in the we did it for every point in the AA region, and then we can calculate what the charge is at every point. And then you do that, or you can calculate it across the entire sample. It is tedious, but you know the data is all there. So then you can put at every point you put the charge, and you see that it breaks up. Right, so all we need to know is that 8 electrons per band and where the Fermi energy is. So that's what this is telling us.
Right, and everything is pinned well enough that as you're exchanging current with a sample, you're not disrupting the structure on a larger scale. You're not, I mean, you don't have phase slippage of the pneumatic structure.
You know, I mean, when we go to different parts, it's not always in the same direction we see. So it doesn't stay in the same direction. So it is kind of a longer crystallographic direction, but it can change direction if you go far away, but it's always there. And when we are away from the magic angle, we don't see this. Yeah. And when we apply magnetic field, the thing goes away above 10 Tesla. So it looks like it's something intrinsic.
Mhm.
Any other questions?
Yes.
Yes.
I mean, but I may not want to, it may take too long. Anyway, one's an easy one. You can really get meters of single crystal graphene.
Okay, the company that you can actually cover a whole wall with graphene, but it's not single crystal. It's CVD graphene. So there are domains.
I see. Okay. Okay.
Now,
Better.
but who cares if you want to make a flat screen or it doesn't matter.
But it depends what you want to use it for. But
Yeah.
I would have been amazed it was single. But the other thing is the way you get the buckling and stuff is from the Van der Waals between your graphene and something else, right? What gave you your strain was that. So when you do the twisting of the bilayers of how come strain doesn't accumulate there as well? Because most of what you talked about for the effect of the twist and the flat bands was the transfer integrals and not any strain, right?
That's right.
So how come Van der Waals is enough to give you the strain that you saw flat bands coming in the first place, and here it doesn't? Because it should also accumulate, right? When you make the Moiré pattern.
When I make a twisted graphene by
when you make a twisted graphene, how come there isn't a strain field there?
This is a very interesting question. So as you know, these AA regions,
right,
are energetically unfavorable. But so there is a price. It does want to decrease in size, but if it decreases in size, it builds up strain. So
yes,
these are small. It's not going to pay to do this. But if you look at this picture here, where I have a very small angle, it's about 0.3 degrees. This, you see? Look at it. This AA region.
Wait. I don't see where you're pointing.
You see the AA regions here? Do you see my screen?
I see your screen. I don't see a pointer.
You see my laser pointer here?
Oh, now I do. Okay, yes.
You see they shrunk tremendously, and there's huge amount of strain, and we measure that is embedded in it because it really doesn't want to be AA. So there is always strain in these things, but it's because of the structure. Now I don't know that this strain is not taken into account when people calculated have shown that it's equivalent to having pseudomagnetic fields. So that probably needs to be added in there. The thing is that at a magic angle, this effect is quite small. So when you go to these tiny angles here, this is about 0.2 degrees or so. Then it becomes a huge, huge thing. And you have these topological channels here that separate AB from BA regions. Yes, so there is, strain is there, but it doesn't prevent us from preparing these layers.
Yeah, that always surprised me that it doesn't lock in.
Because look, this is how we do it. You take one layer, okay, and you slice it in two pieces, and then you lift up the second piece and do parallel transfer on top of the other. And now we have a goniometer. We have something that allows us to twist the top thing and we control it by hundreds of a degree. And then we lay down and we take advantage of the differential sticking. So when you put them, it likes to stick to itself more than to whatever the boron nitride that I picked it up with. So it's kind of frozen in there. Now, if you let it slide, there will be certain directions where it's going to prefer to sit.
Yes, that's what I would have thought. And it goes there. You see that?
And only if you let it slide, otherwise it stays.
Okay. Interesting.